Hello everybody. This is our presentation on pathfinding algorithms using or in video games. Today's presenter is going to be myself, Gustavo. We also have Mariana, Paul, and Fernando. Okay. So this is our table of contents. Table of contents. We're gonna first start off with our abstract, which Mariana is gonna go over that, and then also as well we have our introduction, which states our problem statement. As you can see right there, problem statements, background, or also our background information, which also Mariana is going to go over. Then after that, we have our literature reviews, which individually, each one of us is going to go over our reviews of the literature that we use for this presentation. Then we also have the 4 different types of algorithms that we chose to study, which is going to start with Paul, which Paul basically chose the A-star algorithm. Then after that, we have the genetic algorithm, which Mariana chose. Myself, I chose the DIN-STAR algorithm. And then lastly but not least, Fernando chose the breadth first search algorithm. Then we have Paul explain our results, then the results and the discussion as well that we all had. Then we have our conclusion and our references. Okay, let's move on.
Abstract. Video games utilize advanced algorithms for the purpose of pathfinding. The different algorithms discussed include the A-star algorithm, the genetic algorithm, the DISTRA algorithm, and breadth first search algorithm. These procedures take different approaches, methods, and inspirations to find the best solutions to the paths found in video games. Introduction. Modern-day video games have dynamic worlds with complex interactions and environments. The article, Pathfinding Algorithms in Game Development, delves into Pathfinder algorithms which guide the decision-making strategies and character movement pathways that are found within video games. The aim of this demonstration is to comprehensively understand the pathfinding algorithms by focusing on their structural components and performance processes as well as exploring their optimization. Through a detailed analysis, we will identify and explain such algorithms to further understand game development applications.
So right here, Paul is going to explain his literature review on the A-star algorithm.
Literature review. A-star algorithm. Pathfinding algorithms play a pivotal role in shaping the gameplay experience and computational performances of modern video games. The paper titled Pathfinding Algorithm in Game Development delves into existing research and developments surrounding pathfinding algorithms that are widely used in many modern video games.
Next, we have Mariana explaining her literature review on the genetic algorithm.
Literature review, genetic algorithm. The research article used to explain the genetic algorithm, or GA, was the systematic review and analysis of intelligence-based pathfinding algorithms in the field of video games. This article provided much insight into the genetic algorithm for its unique adaptability and evolutionary approach to problem solving. The effectiveness of the GA was measured by evaluating solutions over generations and has been used in areas such as biometric invention, automotive design, engineering design, and robots. It is mostly used in networking fields, more specifically to develop rerouting protocols.
And after that, we have myself, which is basically explaining my understanding of the literature or the research paper that I chose. And first, let me introduce the premise of the research paper. So the premise of of this research paper is basically introducing all the algorithms that they tested in that actual paper, which, as you can see, we started with the breadth first search algorithm, the A-star algorithm, and also you have DIN-STAR algorithm. These 3 algorithms were tested against each other to find the most efficient between all 3 of them. The test that the researchers did was basically they had one same exact rule with no differences, and they basically saw the information, or they saw the iteration or the usage of the actual algorithm to find the shortest route. And from there, they concluded that the best algorithm to use for this specific route was the DIN-STAR algorithm. After that, we have the literature review for Fernando's, which is going to be breadth first search. So I'll let him explain that.
The BFS algorithm on its own is one of the very first classical algorithms out there. In the article, The Nature of Breadth First Search by Justin J. Holdsworth, it is also clear that this represents an algorithm involved in advance. It is not the best one. For this study, we hope to develop modern-day algorithms and concepts. To simplify, this algorithm involves exploring all nodes in the graph, and through a series of loops and queues, we will eventually get to our goal, which is finding the shortest path to another node or location.
Then after that, we have our technical discussions about, or basically our understanding of each algorithm. We will start off with Paul. Paul is going to explain the A-star algorithm. Let's give him a hand, everybody.
A-star algorithm. The A-star algorithm is widely used pathfinding technique in computer science and artificial intelligence, as seen in the second picture given here, where white square represent an empty space and black square represent the obstacles. The algorithm is designed to find the shortest path between 2 points, considering both the cost of reaching each node, represented by function g of n, and an estimated cost to reach the goal node, represented by the function h of n. Continuing from what I mentioned previously, in the picture I have attached in this slide, the g of n function is represented by a blue number, while the function h of n is represented by a red number. And the importance of these two functions is, for the function of g of n, to ensure that the algorithm prioritizes node based on the actual distance traveled, while the function h of n guide the search toward the goal by estimating the remaining distance. The total estimated cost of reaching the goal node through a specific node is represented by f of n, or it is calculated as the sum of g of n and h of n. This allows the algorithm to prioritize node with lower total cost, potentially leading to more efficient paths. Node with lower f of n values are considered more promising, so it will be explored first. The exploration process continues until the goal node is found, at which point the shortest path is determined, or all possible paths have been explored without finding a solution. So using this given picture as an example, assume node A is the starting point and node I is the goal node. We begin at node A. To decide which node to iterate through next, we add the blue value with the red value of the neighboring nodes and see which one results in the lower number. So for node B, it will be 6 plus 8, which is 14, while node F is 3 plus 6, which is 9. So we know node F costs less than node B, so we move to node F next. But since node F is not the goal node yet, we then now compare the node G and node H to see which one we will be moving to next. After doing some quick math, we can see again that the node G costs less than H, so we move to node G next. And since after reaching node G, we only have one path available to us, so we move to the next node. And since our next node is node I, then we can say that we have reached our goal node. So the advantage of A-star algorithm is it guaranteed finding the shortest path, and it is efficient in static environment. Additionally, it is widely applicable in various domains, including robotics and logistics. Though the performance of A-star algorithm can be impacted by the choice of heuristic function, a poorly chosen heuristic function may lead to suboptimal or inefficient paths. Additionally, the algorithm scalability in dynamic or real-time environment may pose challenges due to computational complexity. Although it is to be noted that A-star algorithm has been applied to many modern game nowadays. Some of the notable example are World of Warcraft, Civilization 6, Age of Empires, and these are used for pathfinding for characters and NPC.
Then after that, we have Mariana explaining the genetic algorithm. Can we please give her y'all's eyes and attention, please?
Genetic Algorithm Part 1. The genetic algorithm was created by John Holland, who was a mathematician in the 1960s. Holland modeled the GA after the human biological system, and he was mainly inspired by the process of natural selection and evolution. The algorithm uses biological terms synonymously with computer terms. Generations refers to iterations, and through each iteration, it will improve the pathfinding solutions or genetics through every evolutionary cycle. More about these terms will be explained as we go through the algorithm. Algorithm procedure process includes initial population, fitness function, selection, crossover, reproduction, mutation, and termination, which is demonstrated in this process below in the image. Genetic algorithm part 2. Initial population. Initial population is the initial input from the algorithm and begins by taking in a set of solutions to the problem. The collection of solutions is referred to as a population, and each solution or individual from this population has a gene. Genes refer to the single variable or parameter that each individual has. A collection of genes would then form a chromosome, which is the individual solution. Chromosomes are usually coded with strings of ones or zeros. The image to the side more distinctly represents the initial population and its terms. So here we can see that there is a 0, which refers to as a gene. And as either a 0 or a 1, a string of these would form a chromosome. And then a set of these chromosomes, such as A1, A2, A3, A4, make a whole population. Next, the fitness function is an evaluation of the individuals and their genes. This step stimulates the process of natural selection by assessing the optimization of each solution and rates it with a score. The score dictates the process of whether the solution is beneficial enough to pass on its traits to the next level of improvement. Following the measure of these scores, two individual solutions will be paired based on their scores to reproduce for the next evolutionary cycle. Scores with higher ratings are most likely to be chosen. Genetic algorithm part 3. Crossover. During reproduction, the chromosome has a crossover point where genes, as zeros and ones demonstrated here, are exchanged among a good solution pairs, which are referred to as parents. They are recombined to make a better individual solution, which gets added to the next population. These better individual solutions are referred to as offspring or evolved solutions. However, mutation might occur during the crossover. Mutation is when bits or numerical values are flipped randomly. Such anomalies do not negatively affect the algorithm. Instead, mutation introduces genetic diversity into the evolutionary process. This prevents the convergence of a single solution too quickly. Instead, it ensures that the population has a wide range of possibilities and promotes the exploration of better solutions. Termination. The genetic algorithm continues to perform generations of this process until there is not enough genetic diversity to consider continuing the cycle. Thus, once the solutions have stopped producing significantly different offspring, it is said that the GA has performed the highest set of optimizable solutions. So here in our images, we can see the crossover points, the exchange of these solutions to create a new offspring. And we also have a mutation which has the flipped numerical values. And this would be the overall process of the genetic algorithm.
Thank you, Mariana, for the great explanation. After that is going to be myself, which I did my literature review or my technical discussion on the DIN-star algorithm. So the little bit of background about this algorithm is it was created in 1959 by Edward Ginstar. Fun fact, actually, It took him, he created this algorithm while having coffee with his wife, and this algorithm only took him 20 minutes to understand or to create the actual theory or the explanation of how this algorithm works. Then after that, we have some real life usage or some real life examples on how this algorithm works or how it's being used. First of all, we have pathfinding in video games, of course. Then after that, we have our our communication network pathways. So what that basically entails is that we have towers that send and receive information from the user, like ourselves and stuff like that. And this algorithm, what it does is finds the most efficient locations to actually set up these towers, and from there we can actually send information and receive information in a much more efficient way. Next, we have prediction pathways. So what that basically tells is, or explains, or says, we basically have this algorithm that tests pathways when it comes to traffic flow and stuff like that. And basically, when to these algorithms basically talk to the stoplights. So let's say, for example, if there is a little bit of traffic in this one specific area, it's going to detect that, and then from there, basically correct the timing of those specific stoplights, so it can make it more efficient and the flow of traffic can be better. Lastly, we have our GPS navigation systems, which is pretty self-explanatory. Basically, this algorithm, or how this algorithm is implemented, is that we have a point A and we want to go to a point B. This algorithm finds the shortest route using the information that is given with the graphs. And then another, or a better way of explaining this actual algorithm is, for example, think of having a weighted graph. Once we have a weighted graph, this algorithm is trying to find the most efficient pathway between these specific points. So these specific points can also be called vertices, and we also have these things called edges. From there, it tries to find the shortest route by computing the information or the parameters or the data that these specific graphs hold, and from there it gives us the shortest routes. One disadvantage about this algorithm is basically having, as I mentioned, these weighted graphs have information. So it could either be characters, it could be any type of data that you would want. But let's say, for example, it's integers. You have, let's say, for example, a positive number of however many meters it takes to traverse, right? What if, let me give you the scenario or the example, what if there's a negative integer? See, whenever the algorithm reads it, it's going to detect it and it's going to say, wait, hold up, I don't know how to interpret this negative integer. So from there, I'm going to stop. So this is a one setback or one negative output or output that we can have, or a problem that can be found in these weighted graphs. And that's one disadvantage for this actual algorithm. Next, we have Fernando explaining the breadth first search algorithm. Let's give it up for Fernando.
In order to be able to explain the BFS or breadth first search algorithm, we need to put it into contrast with a depth first search algorithm. This one involves weighted graphs, which means that if we have a character in city A and we want to move him to city C, of course, there's different transportation methods such as taking a car, bike, a bus, or a plane ticket, and that way we can arrive at different cities. Um, this helps us visualize the different costs of moving to a different city. And so this will be the case for a depth first search algorithm. However, we're going to be studying a breadth first search algorithm, which involves an unweight graph, meaning that moving from one city to another, it's going to take us one operation, and moving throughout any other city is going to take us the same amount, one, without different costs. I have an example here for if we want to move from node 1 to node 0, it's going to take us 1. From node 0 to node 2, it's going to take us 1. From node 2 to node 3, it's going to take us 1. And if we want to move back from node 3 to node 1, of course, we are going to have to go through 0 or 2 and then 1, taking us two different steps. And here we visualize two different paths. The red one will require three different moves, and in contrast, the blue one, it's going to require two. Of course, there's many other paths. These are the two most efficient ones, and we can even make it such that we go to from 1 to 0, from 0 to 4, from 4 to 3, from 3 to 2, and from 2 to 5. And then within the same node, and but this one is gonna take us six different moves. The breadth first search algorithm, although it's one of the oldest algorithms out there, it's not recommended for nowadays use due to its high space complexity, and even then, it wouldn't work for many of nowadays implementations.
Thank you, Fernando, for the great explanation for the breadth first search algorithm. And now I give the floor to Paul to explain some of our results.
Now let's compare this algorithm based on efficiency, structural components, and computational complexity. Considering structural components, each algorithm has distinct features. A-star algorithm utilizes a priority queue and heuristic functions, while genetic algorithm operate on a population of candidate solution represented as chromosomes. Dijkstra algorithm work with a graph structure, and breadth-first search employ a queue data structure for node exploration. In terms of efficiency, the A-star algorithm demonstrate high performance, especially in large environment, while genetic algorithm efficiency vary based on the parameter given, while Dijkstra algorithm and breadth-first search may encounter scalability issues or inefficiency depending on the graph structure. Finally, let's discuss computational complexity. While A-star algorithm balances efficiency and optimality with moderate complexity, genetic algorithm complexity also vary based on parameter once again. Dijkstra algorithm may face high complexity, especially in large graph, and breadth first can also experience challenges in large or weighted graphs. So to conclude, the selection of pathfinding algorithm in video games development still depend on many various factors, and usually it's including efficiency and structural components and computational complexity. By understanding the strength and limitation of each algorithm, developer may make informed decision to further enhance the gameplay experiences they're designed for the player.
Conclusion as a team is that the A-star algorithm is the most efficient algorithm when it comes to finding these routes or pathfinding in video games. It is efficient and it's also memory efficient, so it doesn't take up a lot of actual memory, which in other algorithms would actually take up. Let's say, for example, the DIN-star algorithm. Yes, it's a really great algorithm, and sometimes really they get confused between the DIN-star and the A-star algorithm. But the advantage here for the A-star algorithm is that it's not memory intensive. The DIN-star algorithm would be mostly used whenever you have large input size or a large amount of information in those graphs that you're going to be using. And of course, here are some references. By any chance, are there any questions? No? Then that is our presentation. Thank you again for taking the time out of your day to listen to us. And I hope you guys have a nice, beautiful day.